a ton to cover today, so I'm just going to get right into it. First of all, like, thank you all so much for being here. Like, that is so cool for everyone to show up. Like, I had really, expected to be presenting this to an empty room. So, heartfelt thanks to each and every one of you for being here.
There was genuine fear.
Well,
no one would come.
Don't let them know that much. Like,
so we're very happy you're all here with us.
Yeah. So, this is the NES Code Crash Course. I hope everyone's in the right place. And so today, we're going to be traveling back to the 80s and learning how to make your own NES game using 6502 assembly. It's going to be a fire hose of information. We're going to get through it. I hope to have time for Q&A. If we don't, definitely, let's go hang out. The NES Homebrew developers, shout out to my fellow NES Homebrew developer over here. We're back in the back right corner. I think all of you have already been to the booth, but if you have any questions or anything like that, feel free to come and hang out. I also have contact information at the end, and we'll, get rolling. So yeah, I'm Grayson. You've probably figured that out by now. I am the self-appointed conjurer of code at Sleepy Bits Games. It's fun when you can make up your own job titles. But so I founded Sleepy Bits Games probably about 5 years ago with my wife, Emily.
Yeah, I feel like my job title is everything he doesn't want to do. So it's like...
Guilty.
if there's something he's not interested in, it usually comes my way because I always volunteer to help and do what I can. So
she's modest, but she is a very talented writer and artist. So we've been making games together, for a long time, but made it official about 5 years ago and switched to the NES about 2.5 years ago. And so I've been focused pretty much exclusively on the NES for that time and kind of learning the ins and outs of the platform. And, the good thing is there's a tremendous amount of online resources, some of which we'll be sharing, all of that towards the end. But I just want to get people in this, get everyone excited, kind of know what's out there, and anyone can do this. Don't be intimidated. We're going to go through a lot of code today, but it's going to be okay. We're going to get through it together. So the first thing, yes, that's updating, great. The first thing to know is that everything in this presentation is open source. So if you want to grab that QR code or that URL, I'll put it up at the end as well, but everything that we're going to be talking about today is available there. It's all under an open source license, so you can use it to hit the ground running and get a head start on your next project, because that is what I hope to accomplish today. And so, what are we talking about today? If I can click. Yes. So, we have a game called Game Hunt 2025 that we made specifically for this. And if I throw that to the other screen. Great. So I'm gonna try to do this here. So you can see, here's our little dude, and he has a very specific game in mind. He's at a gaming convention, wants to find that game in all of the vendor tables. It's pretty relatable, I feel like. And so obviously you can walk around. There's just a sea of tables, little party tricks. You can get rid of the thought bubble if you'd like. And you can see, is the game at this table? Oh, well, that wasn't too loud, but that's as loud as we're going to get. If you can't hear it, there's a buzzer that goes off. Yeah, little buzzer to tell you, no, you haven't found it yet. But if we keep going, and oh my goodness, it's a success noise. So a little bit of controller input, a little bit of sound, some animation that I'm probably not going to get to today, but it's all in the project. That's the cool part. And again, that QR code. I don't know if I've ever seen a QR code in an NES game, so here you go. Yeah. So we can do this. Yep. Yep. If I get back over here. So, the hot question on everyone's mind. This is a 6502 assembly talk. Why 6502? Why not, NES Maker or CC65, which allows you to write in C, all of those things. And I am first and foremost here to tell you this is not the only way to make NES games. This is not the easiest way to make NES games by any stretch of the imagination. Great alternatives exist. But I have a few good reasons, hopefully. So first of all, 6502 is compatible with a wide range of retro hardware. Like I do see some other faces in here besides NES devs. So, they can attest to that, but you've got the Apple II, you've got the Atari, the VIC-20, Commodore 64, the Amiga, which I didn't put on the slide. I'm sorry, Amiga guys.
It's actually not a 6502 based.
Oh, really?
Yeah, it's
Great.
6000.
Great. I knew I did that for a reason.
You were spot on.
Awesome pass, Grayson. Thank you. But yes, thank you for that. And of course, the NES. Also, the Super Nintendo can run 6502 in compatibility mode. So it has, limitations, but wide range of hardware. And so I also like to say that there's simplicity in limitation. And so here are literally all of the commands available in 6502. And I get it. That doesn't look so simple, right? However, everything that's highlighted on this slide is in the example project. So you get example usage of a ton of these commands. There are a few that aren't used, but I think everything will shake out in the end. Another good reason, I watched a lot of Reading Rainbow as a kid, and I always liked you don't have to take my word for it. So these are some tweets by Matt Hewson. He's the developer of Witch and Whiz, Super Sunny World, which I don't believe is out yet, but you should definitely give him a follow to see all the cool things that he's working on. But this is just an example of his own experience. And he described he was trying to make breakable blocks and animate those parts that fall out when you break them. And he realized that it was taking too long to do that in C. And so he asked another developer to write the assembly version and actually got a 6x performance gain. Now, I'm definitely not going to sit up here and tell you that, just write assembly, it'll go 6 times faster. That's never, going to hold any water. But the other thing that stands out to me is he talks about coaxing the compiler when he's working with C. And I would rather just, speak directly to the hardware and really, understand exactly what's going on. So hopefully everyone, sees the value in that. Even if I'm not trying to campaign anyone today, but that's my reasoning for sticking with 6502. So speaking of the hardware, here we have the NES motherboard, and you can see that the CPU and PPU are labeled. The PPU is the picture processing unit, probably more commonly these days referred to the GPU or graphics processor. But you can see that we have, how do we actually talk to these things? How do we leverage these pieces of hardware? So the CPU has 3 registers, and if you're new to assembly, registers are kind of the end-all be-all. They hold your immediate values that you're currently working with, and it takes time to move things in and out of memory and things like that. So keeping or making good use of these registers is vital. We have one, it's just called A, that's the accumulator register, and that is your general purpose register. All of your, or most of your mathematics and things like that, a lot of stuff has to go through A. There's also X and Y, which are index registers, or basically counters. And so they're much more suited for offsets, loop counters, keeping track of how many times you're doing something, but you can't actually apply math directly to those registers. So, and we'll see a few examples of working with them. But you've got your program counter, your stack, all that stuff. We won't get too much into that. But I did want to mention the processor status flags. And so these are 7 flags that are packed into 1 byte, and they represent negative, overflow, break, decimal, interrupt, 0, and carry. And so what on earth does that mean? So you can check these flags after doing various operations to understand the results of those operations. So if you do like a subtraction, for instance, and the result was negative, both the negative flag, actually, I'm gonna correct myself, the negative flag will be set. Carry is the opposite of borrow, which we'll see in just a minute. So if carry was clear, for instance, that would mean you still have a remaining borrow. Hopefully I'm not triggering anyone with elementary school memories of math class, but we'll refresh all of that. So the PPU is kind of interesting because you basically have this, pseudo interface to talk to it with. And what I've done here is included the addresses and the kind of canonical names. And in the example project, I have an include file that just provides a mapping to all of these. So you don't have to remember, like, oh, okay, 2005 is the PPU scroll register. You can actually just write straight to PPU scroll, things like that. So a little bit easier. One other thing to note is do not ever use the OAM data. Now, what is OAM data? It has to do with sprites. We'll talk about OAM. It stands for Object Attribute Memory. But basically, the OAM data register can corrupt your sprites. So it's much better to do a direct memory access during vblank instead. Getting a little ahead of myself, but that's why I wanted to mention that register, but now we're forgetting about it. So we also have the APU, or the audio processing unit. Now I know, what some of you are saying. You just told me that was the CPU. Well, it is. So Rico actually removed some functionality from the MOS 6502 and replaced it with audio capabilities. Specifically, the decimal mode is not available on the NES. So what are those audio capabilities? Well, we have 5 sound channels. And these are different ways to produce noises on the NES. You have 2 pulse channels, or they're sometimes called wave channels. They're kind of the bleeps and bloops that you're kind of familiar with. We have 1 triangle wave channel, which is typically used for lower sustained bass notes in music and things like that. We have the noise channel for explosions and buzzers, like the buzzer we maybe heard in the example. Sometimes percussion, like kick drums or snares. There's several different frequencies available. And we also have a delta modulation channel for sample playback. Now, samples are really expensive, both in terms of storage and actual CPU playback. So they weren't used that often, but you can see them in like Double Dribble. The NES game has a pretty infamous use of saying the words double dribble when you get to the main menu. So that's just one example. Excuse me. I like to use them just to add kind of that retro flavor to games, but they are very expensive. So you can't get anywhere without memory, right? And so there are 2 kilobytes of memory available for the CPU and the PPU. And 2K may not seem like very much, but I'm sure if you talk to an Atari 2600 programmer, they would kill for 2K. So one other note, you probably can't see it here, but the CPU does not have direct access or direct lines to the PPU memory. So the PPU has to be involved whenever PPU memory is updated. So anytime you're loading new graphics or things like that, it does take up both the CPU and the PPU. So just something to note, the PPU can't do that on its own, nor can the CPU. One other piece of hardware that we have is obviously the controller. And so each frame we're going to read the button state. And to do that, we actually have to send 2 commands to the controller first. It's what is called strobing. And so the first signal is the high voltage that says, start collecting button state. And so it will start filling up its own buffer to reflect which buttons are pressed, which buttons aren't. And then we send a low voltage signal down the wire to say, okay, lock those values in, I'm about to read them back. And so, it's funny because, or I think it's funny, there are 8 buttons on the NES. There are 8 bits in a byte. So how many reads does it take to read all of the button data on the NES? Of course, it's 8. So the reason for that is that you also get information for accessories, like the zapper, the multi-tap, things like that. All of that's actually being read back as well. We're kind of tossing it aside for the demo, since we don't really care if you're clicking the zapper during the demo or things like that. But just know that that's kind of like the historical reason why that's true. And finally, something that is no longer true, but definitely was back in the day, you could have custom hardware in the cartridges. And so everything we're going to be talking about today is from the NROM mapper, or mapper 0, for the emulation crew, basically, went through and numbered all the mappers. But this is the most basic NES configuration, but it's used for a ton of games, like Balloon Fight, Donkey Kong, Duck Hunt, Excite Bike, Ice Climbers, Super Mario Brothers, and many more, quite honestly. I was just naming off first-party titles. So, as the NES lifecycle went on, games got more complicated, so did the cartridge hardware. That's how they achieved the complexity that they were able to do. But today, we're only going to be talking about the NROM. And so what does that mean? So we have 8 kilobytes of graphics storage. We have 16 or 32 kilobytes of program ROM, which is either code or data. I labeled the CIC chip over here, which was basically anti-piracy. Luckily, we don't have to deal with that. It talks to the console by itself. We don't have to do anything to enable that. But we also have a soldering pad on here for name table mirroring. And so, what on earth does that mean? Well, the NROM provides basically 2 screens of graphics. And so you can arrange those screens either horizontally or vertically. It's generally used to support different scrolling types. Like Mario, you're scrolling left to right, so you're going to be in a horizontal configuration, or what they call vertical mirroring. And so that's just saying that, like, if we scroll past the bottom of the screen, we will start to mirror the top of the screen again. The other option, obviously, is the other way. And so, something like Ice Climbers, for example, you're climbing up the mountain, you're scrolling vertically, so that's going to be in horizontal mirroring. And so I believe, this picture actually is bridging the horizontal solder pad. So it's actually doing vertical mirroring. I believe this is a picture of Super Mario Bros., if I remember correctly. And one other thing to note is that all of this data has to, it's inherent to the hardware, but we have to tell emulators about this somehow. So what they've devised there is a header. There are 2 different header formats, the iNES and the NES 2.0 headers. Basically, these were devised by emulator developers to encapsulate all of this data. But they were actually used in official Nintendo products at some point as well. So Animal Crossing was an early example of, you had like the NES console in Animal Crossing. You could go and play the games. That was actually using the iNES header that was originally conceived by external emulation developers. That's all I'll say about that. But So one other thing that I want to cover real quick, and maybe everyone already knows this, so I'm going to be pretty quick about this, but different number systems. So one of the nice things about CA65 is you can use any number system anytime you want. So for things like tile numbers or tile IDs, it might make more sense to use hexadecimal. For positions, you might want to use decimal. It's basically just whatever is, you're most comfortable in. It's all going to compile to the same thing in the end. So decimal, just as, kind of review, base 10, so 0 through 9. There's no CA65 prefix for this. So an example, if you just saw the number 240 in code, you know that that's a decimal number. Hexadecimal, 0 through 16, 0 through 15, 16 possible values. I like to joke that, we use decimal because we have 10 fingers. Obviously, there are 16-finger aliens out there using hexadecimal, but actually it's just a very nice shorthand for hexadecimal, or for binary values. You can represent them in hexadecimal. Makes it a little more readable. So if you split 4 binary values into a single hexadecimal number, you get a nice shorthand mapping there. So it has the $ as the prefix. The example, $F0, great game. You also have you can use pure binary for everything, and that has the percentage symbol. So if you had 11110000, fun fact, 240, F0, and 11110000, they're all the same value. So let's look at some 6502 instructions. These, we're gonna go pretty fast through these, but I think they're pretty understandable. So these are mnemonics to help you remember what's going on. So we have, like load and store. So whenever you need to pull something into a register or store something out to memory, that's when you're going to use things like this. So like we mentioned before, you have A, X, and Y. So of course we have different flavors of load for A, X, and Y. Same with store. You can store from A, X, or Y. Like I mentioned before, we have, you can only do, some of the math operations on A. So we also have transfer operations. And just remember that those are always transfer this to that. So for example, TAX, you are transferring A into X. And we'll see example usage of all of this in just a moment. Maybe review, maybe new information, but we have these binary operators, binary AND, binary OR, and binary exclusive OR. And so apologies for putting truth tables in this presentation, but the only thing to really, to glean from this, if you only remember one thing, just remember that AND is useful for clearing bits. So if you clear something with 0, you'll always know that it's 0. OR is useful for setting bits. So if you OR something with 1, it's always 1. And XOR is useful for flipping bits. So if you XOR something with 1, it's always the opposite of its previous value. So like I mentioned before, the carry bit is something we deal with a lot. And so we have specific instructions for clear carry and set carry. And so then our add and subtract methods always use carry. There is no way on the 6502 to add or subtract without taking into account the carry flag. So one way to think of this is when you do an ADC, which stands for add with carry, add with carry. Just remember that it's A plus whatever parameter you're providing plus the carry bit. So it's typical that you clear the carry flag before doing an ADC. And the same way, like I mentioned, borrow is the opposite of carry on the 6502. And so we usually set the carry flag before we do a subtraction. There are actually some pretty famous bugs in commercial NES games because they clear the carry when they meant to set the carry on before doing a subtraction. If you've ever seen speedrunners zipping in Mega Man, it's actually because they did a clear carry when they meant to do a set carry. So just a fun historic note. There are also binary shifts. We're not going to go too deep into this, but just know that if you have a bit field, a binary shift is basically just moving everything one direction or the other. And so the last letter of the mnemonic tells you which direction you're going. So just running down the list, that is arithmetic shift left, logical shift right, roll left, and roll right. And so why do we have two different versions of going left and right? Well, it has to deal with how the carry flag is updated in these cases. I'm going to glaze over this just in the interest of time, but I will have links to the documentation at the end, which spells everything out much better than I could. And the only thing to really know about shifts right now is that they can effectively multiply or divide by 2. So if you think about how the bits, are manipulated, shifting to the right is basically a divide by 2. Shifting to the left is basically a multiply by 2. You can do this repeatedly to multiply by powers of 2 or divide by powers of 2. But the 6502 does not have multiply and divide opcodes or instructions. So if you do need, arbitrary multiplication or division, you're, writing that or copying that most likely from an existing implementation, but it will be, a set of commands. It will be expensive. There is no just doing that in hardware. At least on the NROM. There is a mapper called the MMC5 that offers multiplication, but that's not for us, not today. We also have increment and decrement operators for the counter variables or the index registers that we have. So obviously increment X, increment Y, decrement X, decrement Y. These are common for loops when you set a value and you count down from that, or things like that. So these can also be used for offsets into data. So if you say my data starts here and I need to read the first 10 bytes, you can increment X up to 10 and do what you need to do with those bytes as you step through them. We'll see examples of that as well. I know I'm glossing over a lot in this, but hopefully everyone can go back and kind of revisit this along with the code and see how everything kind of gels together. So branching instructions. So if you're familiar with higher level languages, this is basically how we make decisions and how we do like if-else statements. And so just kind of going down the line, we have branch if carry clear, branch if carry set, branch if equal, branch if not equal, branch if plus, branch if minus. And you'll notice like these correspond to those processor flags that we mentioned earlier. So basically you'll always be checking those processor flags after an operation to make a decision using these. We also just have an unconditional jump statement. So we can say, unconditionally jump to this address next and start executing from there. Excuse me. So this can be useful for chaining together, groups of logic that always operate one after the next. And so, they can also be useful for like the else statements. So if we were testing like, if X is 0, or, if A, let's use A instead, I'm sorry. So we could do a branch of equals, which is the same as saying, is this 0? It's kind of shorthand for is it 0? That's what your equals command will be. So if A is 0, branch here, your else statement, so if A is not 0, jump to here. And that's basically your if-else structure that you'll use a lot. We also have jump to subroutine. So our code can be, kind of partitioned into subroutines, or, you can think of them as methods, functions. They're all basically the same thing, but JSR, or jump to subroutine, will do all the updating to the stack that you need to do so that you can actually return from that subroutine and get back to where you were. So jump is a one-way operation. If you don't know where you came from, you can't get back there. But JSR, you can always return from subroutine, or RTS, and get back. So it's like a function call. You can go out and come back. Okay, no more instructions, I promise. Maybe. So let's talk about the program flow of an NES game. So we have what's called vectors, which are basically just addresses that we jump to in specific cases. So we have the reset vector, which is responsible for initialization. And that is jumped to anytime the console turns on or anytime you hit the reset button. And usually that executes, we do our initialization, and then we fall into the game loop, which is typically an infinite loop that just updates the game logic every frame, does what it needs to do for the gameplay, and prepares graphics updates. And I say prepares graphics updates because we can only do those, for the most part, inside the time frame that's called v-blank. And so back in the day with CRT televisions, the electron gun was actually scanning out the picture of your game, and it needed time to return from the bottom right to the top left of the screen. And so that's the time that we have to update graphics, basically. And so that's what's called v-blank in this case. And we know that's happening because of the NMI vector. So NMI stands for non-maskable interrupt. And so this is code that basically yanks us out from wherever we were when it happens, does something, and then returns us back to where we were before the interrupt happens. And that's why it's called an interrupt. It interrupts execution. And you'll typically need to push or save off the values of any registers that you plan to use in the interrupt, because you don't want to stomp on values that were being used outside the interrupt and then pop them back off the stack. They're typically pushed on the stack and then popped back off before returning from the interrupt. The one thing to note here is that the processor flags are actually pushed and popped for you. And so that's something that just automatically happens with the interrupt. We also have general purpose interrupts, which is just on the IRQ vector. We won't be using those today, so I'm going to gloss over them, but there are several different cases for that and ways of kind of figuring out what just interrupted me, but they all go through the IRQ vector.
Only one more slide of instructions, and then we get to code.
Spoilers.
You chose to drink.
Yeah. No, and I know this is a fire hose of information. So yeah, just real fast, talking about the memory map. So we have the 0 page. So if you think of memory being stored in pages, and pages are just arrays of 256 bytes. So when that top byte of the address is 0, we're in the 0 page. And it actually requires one less byte to access things from the 0 page. So this is where you want to put all of your fast access variables, things that you access, multiple times a frame, ideally, things like that. It's your most precious memory because it's your fastest memory. From 1011 to 10FF, that's reserved for the stack. So the 6502 actually requires that the stack be in that range, and it grows down. So basically what that means is you can stuff other things in that memory if you know you're never going to have a stack that deep, but that's something pretty advanced and something we definitely won't be doing today. So from 0200 to 02FF, we have what I like to call the OAM shadow. Like we talked about before, whenever you see OAM, that's object attribute memory, that's for sprites. And so basically this is a copy for the CPU. And we'll do this with other variables as well, but this is the CPU's copy of the next sprite update. So while the previous update is being scanned out by the PPU, we can write to this and then do a DMA, or direct memory access, from this copy straight into the PPU to update all the sprites at once. And then we have unused memory from 0300 to 07FF. So much more memory to add all sorts of features to your next NES game. So finally, it's been a lot of talk. Let's take a whirlwind trip through some code. So like we mentioned before, here is your INES header, and we're basically specifying, we need the minimum amount of PRG ROM and CHR ROM. We're using mapper 0 and in a vertical mirroring configuration, like we saw on the cart picture, basically, is all of this. And then we have the names of our vectors, so very original names, NMI, reset. We actually zero out the IRQ vector because it's never called, so it doesn't really matter what we put there, but generally you zero that out to kind of say, I'm not planning to use this. So we have a few zero-page variables. And so I'm really going to start jetting because we need to pick up the pace. I apologize. But basically, these are more like PPU copies of things, things like that. We'll see how they're used, but the only thing to note here is we're letting the linker decide the layout of memory. Each time you see the .res, that stands for reserve this number of bytes. So, like the current button state, for example, I call joy1 current, and that takes 1 byte. Joy1 previous also takes a byte. We'll see how to use that. Some constants, just to keep ourselves sane. So we need to, know where that cart is, for instance. So the screens are called name tables. We are in screen 1. So if you have 0, 1 on the screens, we're in screen 1. We're at X location 80, Y location 176. We also can group constants into what's called enumerations. And so for the animation code, we can have different directions or basically standing still. So we have a none as well. But all of those are related to directions, so we can group those into an enum. So our reset vector, like we said, is responsible for initialization. And this is the standard NES initialization code. It's used in a lot of retail games. It's used in a lot of homebrew games. So unless you have a specific reason to change this, you should probably just stick to the tried and true. So PPU initialization. So the graphics chip actually takes about 2 complete frames to warm up to be ready to accept instructions. And so this loop that we see here, first we just clear the V blank flag, but then we actually do what's called a bit operation, which will copy that register into the status flags. So this is shorthand, and we just check to see if we're in V blank yet. And so the V blank flag actually lines up with the negative flag, so that's why we use a branch if plus. And so that colon minus basically just means go to the previous unnamed label, which is that colon before the bit command. So it's just a busy loop, basically right there, waiting to get that signal from the PPU. So after we know the first frame is done, then we can go ahead and initialize our CPU variables. Hopefully this all makes sense. I'm gonna go over it pretty fast. And then we jump into init audio. And so init audio is pretty simple. We just zero out all of the things related to the first square wave and the noise channel, which are the 2 noise channels we expect to use. And then we actually need to enable pulse 1 or wave 1 and noise after everything is disabled, so we know we won't get any random noises when we enable them. and we set that, we store that in the sound channel register to give that to the APU as well. So PPU initialization part 2, we do the exact same thing again. We do that same loop, and then there are 3 methods: initialize palettes, initialize name tables, initialize sprites. So this is the NES palette. It can produce a total of 54 colors. You can't actually define your own RGB values. They have to be from this, and the console actually generates it directly as video signal. So nowhere is there like a canonical set of NES colors. A lot of work has been done to identify these colors. Excuse me. This particular set of colors was researched by a guy who goes by Firebrand X online. It's one of the most ubiquitous ones. Yes. And but it's the one that I basically use for all my development, and encourage people to use as well. So this is called Smooth FBX. Yes. So and also red, which is interesting because Mario is red. So lots of blues, lots of greens to choose from, but not a lot of like red, orange, yellow. It's
I guess Mega Man really was made for the NES.
yes. So how do we define this? How do we use this? So the NES has 2 layers: background layer and sprite layer. So the backgrounds have 4 palettes, sprites have 4 palettes, but basically the background all share a single background color, so the backdrop behind everything is 1 color, and then they each get 3 colors to choose from. And so you can see this is the palette viewer from the Messen emulator, and you can see I'm just using 00 for unused slots. But basically, we have 1 background palette and 3 sprite palettes that we're going to choose from. And so I should mention, sorry, that on the sprite palettes, the background palette is actually just used for transparency. So to make cutouts around sprites and things like that, you would just define to use the background color or the 0 index. So this is pretty simple, just a mapping. This is from the data.include file from the project. But you can see very easily how these bytes just map over. It's the same values, just in this this notation. And so basically, we have to know where to put these palettes. So all palette entries live at 3F00 on the PPU. And so addresses are 16-bit on the NES. Yes, there are 16-bit values on the NES, contrary to popular belief. But that's basically done by writing 2 bytes in order, always high byte, then low byte, which is interesting because 6502 addresses are generally stored low byte then high byte, but that's not how it's done with the PPU. So this code is basically saying at 3F00, store these 32 values. And so like we talked about before, we initialize X to 0, or we load 0 into X, and then we have the palettes label from the previous slide, we're offsetting by X, and then we're giving that to the PPU data register. And so that's giving this information to the PPU 1 byte at a time until we've transferred 32 bytes, basically. Pattern tables. Really running out of time here, sorry. So pattern tables are 1 kilobyte arrays of tiles that are basically references back into those palettes. And so you can see here the NROM format provides 2 pattern tables. You can use 2 pattern tables at a time on the NES, so that works out. But basically, you can see that we have 1 pattern table for sprites and 1 for backgrounds, and kind of how they're laid out. And the animation code actually takes advantage of how these frames are laid out and does some little tricks to know, like, along with that enum that we looked at previously to know that, okay, the order is up, down, left, right. Things like that, always offset by 2 when you're flipping between the frames. Things like that. You can also see the QR code and the thought bubble, all of that good stuff. So name tables. These are basically screens on the NES, like we talked about. And so they're 960-byte arrays that define background layouts. And so that works out to 32 by 30, 8 by 8 tiles. So here we see that it looks like there's actually 4 in the tile map viewer, but remember we are mirroring 2 of those. So there's several tools that allow you to lay this graphics data out how it should be. I'll share links to those at the end, but we won't be going too much into the format of these, but it's also important to note attribute tables. So attribute tables are how you control the colors in the background. And there are many fewer of these than there are tiles in the background. So anyone that's played, a fast-scrolling NES game has probably noticed the strange colors on the edges of the screen as they scroll on and off. And that's actually due to these attribute tables that control the coloring of multiple tiles. So it's an 8 by 8 grid. Each value controls a group of 4 by 4 tiles, and each value controls a group of 2 by 2. So it's impossible to change the color of a single background tile on the NES unless you have a very advanced mapper. So this is a snippet from init nametables in the example project, and it's using what's called a pointer. Definitely don't have time to get into pointers today. They're often confusing to any new programmer, but basically just think of it as if a variable holds a value, a pointer holds an address to a value. So basically on the 6502, I mentioned the pointer or addresses are usually stored low byte then high byte. So you can see the syntax of basically pound sign and then a less than sign, which means give me the low byte of this address. And so nametable 1 is a label that we have in the program that basically just has all the bytes that we need for the nametable. And so we do the same thing for the high byte. We have our pointer set up. And so this is kind of tricky code. So we initialize x to 4, we initialize y to 0. And so what we're going to do is we're going to go through every value of y, so 256 values. We're going to do that 4 times. And each time we increment y, we're going to take that value and we're going to give it to the PPU just like we did before. But when y is back to 0, we actually decrement x and we do the whole thing again. So what on earth are we doing here? Well, if you think about it, a name table, which is 960 bytes, plus an attribute table, which is 64 bytes, ends up 1,024 bytes, or 256 times 4. So this is just a very nice way to take a name table that's already laid out in your ROM and basically copy it to the PPU. So it's not necessarily important that you understand every line to this right now, but just know that this can load any arbitrary name table. So definitely reuse this. So we've been talking a lot about object attribute memory. What on earth is that? So it's an array of 256 bytes that describes 64 sprites, basically. So 4 bytes per sprite. And those bytes are, and in this order, the Y position of the sprite, starting from the top of the screen. And one really useful gotcha is that this is actually offset by 1 pixel based on how the PPU goes and fetches the sprite tiles. So that means that it's actually impossible to start a sprite on the first scan line of the NES. Fun fact. We have the tile index, or the tile ID, and that's basically referencing into the pattern table which tile you want associated with this sprite. We then have a bit field of attributes, and so this includes which palette this sprite should use, the priority of this sprite, whether it's in front of or behind the background. And then we can also flip the sprite vertically or horizontally. You can't flip backgrounds on the NES, but you can flip sprites. And then finally, the X position, which starts from the left side of the screen. And in the same way that it's impossible to start things on the first scan line of the screen, you can start things on the first column of the screen, but you can't start anything before that. That value would actually wrap to the right side of the screen at that point. So it's impossible to start anything before the first column or actually the second scan line. And I just got the 5-minute symbol or the gesture from behind us, so I think I have 9 minutes, but we'll see when we get thrown out. So yeah, this is just a look at the Messen emulator, giving you a view of the object attribute memory, shows you how the sprites are split up, how they're positioned on the screen, all of that good stuff. And so here's a good example of the mixed number systems that I was talking about earlier. So this is saying that we want to lay out the player at Y position 111, but we want to use tile 6, and we want it at there are no attributes. So first palette entry, no flipping, priority in front of the background, all pretty sane defaults, and we want it at 120x. And so you can see the tile ID is hexadecimal, the positions are decimal, just because I think it's more intuitive. And so we have all of these defined, one after another in the data.include file. So this is just a little bit of an example. And then remember, we have that OAM shadow, so we have our own copy of the sprite updates. And so this code is basically just copying, the static initialization ROM, or the initialization ROM contents into that shadow to then be pulled over to the graphics update. So, let's see. Since we only have a few minutes, I'm just going to go lightning speed through this. I apologize, but all of this is, fully documented and all of that. So hopefully, you don't mind digging through it a little bit. But I know it's a lot of information. So basically, we set up the PPU control register to based on these bit flags to say we're ready to rock and roll, we're ready for v-blanks, all of that. Finally, initialization is complete. So the game loop. The first thing we do is we say, okay, now that we're ready for a v-blank, let's wait for one. And so like before, we just do that busy loop, and the v-blank will actually tell us when we've been in and out of that interrupt, basically. We then jump to the handle input subroutine and the update animation subroutine, and then we do the whole thing over again. So if nothing else happened, this would just go on till the end of time. So read input is actually all straight from nesdev.org. Fantastic resource. But I will be skipping over it just because there's nothing really new here. But basically, like we said, we strobe the controller, we pull out the bits we're concerned with, we put them in our Joy 1 current, and we do that 8 times to get those 8 bits. So to then test that, we use we AND the current buttons with basically masks to see if the button we care about is pressed. So in this example, we're testing button A, which is defined in the program as the specific bit field that we need it to be. And we check, not only is A currently pressed, but was it just pressed? So we don't want this firing every frame that A is down, because that would, sometimes you want that for like directional input, like if you're walking to the left or right, you just care about if it's down. But some other times you actually care about bouncing and debouncing. So this is an example of that. Yeah, I think for the interest of time, I'm actually going to skip the rest of the code. I really apologize. But it's all here. It's all commented. We have check code. This is, logic to play the success beep. We have logic for the failure buzz. Some example code on moving the player. These basically follow the same things as those other things. Update animation, graphics, oh my goodness. So, yeah. Hey, look at that, we made it. So I also have a list of basically, the required tools for this. I highly suggest the CC65 suite. The Meson emulator has a lot of great built-in stuff. And of course, your favorite text editor. There's some optional tools. You can check all of those out. Here are some references for you for, different things. Here are a few like online tutorials that can explain everything a lot better than I can and have a lot more time. But and finally, here's just a couple technical YouTube channels that I wanted to call out that do a really good job of not only introducing these concepts, but Displaced Gamers actually goes through code walks of some of your favorite games to kind of see like how they did things, and a lot of times expose bugs as well, but they're really entertaining. So.
Is this presentation in your Game Hunt?
Yes. So it's actually included in the GitHub as well. Yeah, as a PDF. So, yeah, and I'll put that QR code back up in just a second. But obviously, you can find us Sleepy Bits Games just about everywhere. I'm either Chimbraka or Grendel on various things. Long story there. Or feel free to always email me, just Grayson at Sleepy Bits Games. Love to hear from anyone, everyone. That'd be awesome. And thank you. Oh, is there no way to go back to the original?
Could you put
Oh,
your
no.
social back up there for X?
Yeah. So I'll let people grab that real quick, and then I'll go back to the QR code as well.
Which do you prefer for this kind of content?
I'm not picky. Either one is great, but thank you. And oh,
Well, sorry.
oh,
You go
sorry,
back once.
sorry. Yeah, sorry. So there's all that. Sure.
Yeah.
And then there's the QR code and the GitHub for this, and you don't even have to use Git really. You can just download a copy of everything from the repo. So don't be intimidated by that. But I really apologize that everything was so rushed. I probably should have chopped this down a little bit more, but there's so much to cover, but I highly encourage that everyone, like, there's so many resources out there and so many helpful people. Like, it's an awesome community. So definitely don't be intimidated, and don't be shy.
Yeah. I hope you learned something today. So.
Thank you.
Awesome. And thanks everyone for coming
Yes.
again. That's
Thank you.
so awesome of all of you.